Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra chapter Eigenvalues and Eigenvectors, lecture number 9, in which I will solve some problems to find eigenvalues and eigenvectors. Now we solve a problem. Problem is determine the characteristic roots and characteristic vectors of the matrix A. A be the given matrix. Now we solve this. The characteristic matrix will be A minus lambda I. A is 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 minus lambda I is unit matrix 1 0 0 0 1 0 0 0 1 implies that A minus lambda I equal to 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 minus, we multiply lambda with each element of unit matrix. Here we get lambda 0 0 0 lambda 0 0 0 lambda. This will be equal to 8 minus lambda minus 6 minus 0 minus 6 2 minus 0 2 minus 6 minus 0 minus 6 7 minus lambda minus 4 minus 0 minus 4 2 minus 0 2 minus 4 minus 0 minus 4 3 minus lambda. This is number 1. Therefore, characteristic equation will be determinant of A minus lambda I equal to 0 implies that determinant of 8 minus lambda minus 6 2 minus 6 7 minus lambda minus 4 2 minus 4 3 minus lambda determinant equal to 0 implies that this is 8 minus lambda. Here we get 7 minus lambda multiply 3 minus lambda minus this 16 minus 16. Now we take this minus minus plus 6. Here minus 6 multiply 3 minus lambda minus 6 multiply 3 minus lambda minus 2 multiply minus 4 minus 8 and minus is plus 8 plus 2, this is 6 multiply 4 24 minus 2 multiply 7 minus lambda equal to 0. By calculating, we get this lambda to the power 3 minus 18 lambda square plus 45 lambda equal to 0 implies that we take common lambda square minus 18 lambda plus 45 equal to 0 implies that lambda square minus 15 lambda minus 3 lambda plus 45 equal to 0 implies that lambda, here we take common lambda minus 15 minus 3 lambda minus 15, this equal to 0 implies that lambda multiply, here lambda minus 15 common from these two terms, and here remains lambda minus 3 equal to 0 implies that if lambda equal to 0, we write lambda equal to 0. If lambda minus 15 equal to 0, then lambda equal to 15. If lambda minus 3 equal to 0, then lambda equal to 3. Therefore, characteristic roots of matrix A are 0, 15, 3. Case 1. For lambda equal to 0, let x be the characteristic vector then Ax equal to lambda x implies that Ax minus lambda Ix equal to 0 implies that A minus lambda I matrix x equal to 0. Let this is number 2, this is number 3. Using 1, we get A minus lambda I, and capital X is column vector x1, x2, x3, and right side 0 vector, 0 matrix, 0, 0, 0. This 0 real number and this 0, 0 matrix or 0 vector. This is number 4. Putting lambda equal to 0, we get here 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3, here x1 x2 x3 equal to 0 0 0. Here we interchange third row and first row by R1 R3. Here 2 minus 4 3 minus 6 7 minus 4 8 minus 6 2 x1 x2 x3. Here 0 0 0. Here we have to make 0, here we have to make 0. So by taking R2 in place of R2, R2 plus 3 R1, and here in place of R3, R3 minus 4R1. Here we get 2 minus 4 3. Here 0, here 0. Here will be minus 5. Here will be 10 minus 10. Here x1, x2, x3. And here 0, 0, 0. Here we have to make 0. So in place of R3, we take R3 plus 2R2. Here left side 2 minus 4 3, 0 minus 5 5. Here we get 0. Here also we get 0. 0 0 0. Here x1, x2, x3. 0 0 0. This is number 5. Since the coefficient matrix contains 2 non-zero rows, therefore rank of the coefficient matrix equal to 2. Number of unknowns, here x1, x2, x3, 3. Therefore number of linearly independent solution equal to 3 minus 2 equal to 1. Therefore there will be only one linearly independent eigenvector corresponding to eigenvalue lambda equal to 0. From 5 we get 2x1 minus 4x2 plus 3x3 equal to 0, and we multiply this. 0x1 minus 5x2 plus 5x3 equal to 0. This is number 6. This is number 7. From 7 we get x2 equal to x3. This is number 8. Taking x1 equal to 1 and using 8 in 6 we get here 2 multiply 1 minus 4x2 plus 3x2. Since x3 equal to x2 in 8 equal to 0 implies that 2 minus x2 equal to 0 implies that x2 equal to 2. This is number 9. Using 9 in 8, we get x3 equal to 2. This is number 10. Therefore, eigenvector x corresponding to eigenvalue lambda equal to 0 will be capital X equal to x1 is 1, x2 is 2, x3 is 2. This is number 11. We know that if x is an eigenvector corresponding to eigenvalue lambda, then kx will also be eigenvector corresponding to eigenvalue lambda. K be any scalar. Therefore, kx equal to k multiply vector 1, 2, 2 will be the eigenvector corresponding to eigenvalue lambda equal to 0. Now case 2. When lambda equal to 15, by putting lambda equal to 15 in matrix equation 4, we get here lambda 8 minus 15, here lambda 7 minus 15, here lambda 3 minus 15, and this will be the equation. Now subtracting 8 minus 15 is minus 7, 7 minus 15 is minus 8, 3 minus 15 is minus 12, and now here we want to make minus 1. So if we take in place of R1, R1 minus R2, minus 7 minus 6, here 1 we will get, and other row remains same. Now we want to make here 0, here 0. So we take in place of R2, R2 minus 6 R1, and in place of R3, R3 plus 2 R1. Here we get 0, here we get 0, and here also 0, here also 0. So here we see that number of non-zero rows of the coefficient matrix is 2. Therefore rank will be 2. Rank of the coefficient matrix will be 2. Hence number of linearly independent solution will be number of unknowns 3 minus rank of coefficient matrix 2 equal to 1. Hence there will be only one linearly independent eigenvector corresponding to eigenvalue lambda equal to 15. Hence equations are from here minus 1 x1 plus 2 x2 plus 6 x3 equal to 0. Here minus 20 x2 minus 40x3 equal to 0. From last equation we get that x2 equal to minus 2x3. Putting x3 equal to 1, we get here x2 equal to minus 2 and here x1 equal to 2. Therefore, eigenvector will be x1 equal to 2, x2 equal to minus 2 and x3 equal to 1. Hence, eigenvector corresponding to eigenvalue lambda equal to 15 will be k multiply this eigenvector, where k is any scalar. Now we deal case 3 for lambda equal to 3. Putting lambda equal to 3 in matrix equation 4, we get this equation. Here we want to make 1 or minus 1. So we take here by R1 in place of R1, R1 plus R2, 5 plus minus 6, minus 1. So here minus 2, here minus 2, other remains same. Here we want to make 0, here also we want to make 0. So in place of R2, we take R2 minus 6 R1, and in place of R3, R3 plus 2 R1, and we get this equation. And now we want to make here 0. So in place of R3, we take R3 plus half R2. So here we get 0 and consequently here also 0. Here we see that number of non-zero rows of the coefficient matrix be 2. Therefore, rank of the coefficient matrix is 2. Here number of unknowns be 3. Therefore, number of independent solutions equal to number of unknowns minus rank of the coefficient matrix. Means 3 number of unknowns minus 2 equal to 1. This will be the number of independent solutions. So, number of independent eigenvectors will be 1, corresponding to the eigenvalue lambda equal to 3. Now, equations, we may frame these equations. We multiply first row, multiply first column, minus x1 minus 2x2 minus 2x3 equal to 0. Now, second row multiply first column, 0 multiply x1, 0, 16 multiply x2, 16 x2 plus 8 multiply x3, 8x3 equal to 0, and last row 0 contains 0, 0 multiply x1 equal to 0, 0 multiply x2 equal to 0, 0 multiply x3 equal to 0, and right side 0. So we solve these two equations. Here from second equation we get x2 equal to minus half x3. Let x3 equal to 2, then x2 equal to minus half multiply 2 means minus 1. Putting x3 equal to 2, x2 equal to minus 1 in first equation, we get this value, and x1 equal to minus 2. Therefore, vector x equal to column matrix x1, x2, x3, x1 is minus 2, x2 is minus 1, x3 is 2. So, eigenvector corresponding to eigenvalue lambda equal to 3 will be k multiply this x. This x is this column vector or column matrix, where k is any scalar. So, we get the characteristic root or eigenvalue of the matrix, and we also get eigenvectors corresponding to these three eigenvalues. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button, and if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.